but I'm not going to tell you that. I'm going to tell you how it works. This. Quickly stolen off the internet picture of the gateway arch. All right, thank you very much. I'm going to talk about APLicative programming with Naperian Functors. There's a joke in there that says APL-ish kind of programming model. And this is a talk I've given a couple of times before, and Dominic suggested this will be a receptive audience for it as well. So some of you will have seen this, and I apologise for that. It hasn't changed very much recently. So let me remind you about of history. So APL, this language by Ken Iverson from 1962. I mean, the idea is probably older than that. The A stands for A. It's a programming language, but it's often read as an array programming language. The USP of APL is that it treats arrays seriously as values and lifts as much as possible all the usual operations from scalars to arrays. So where you have a scalar operation like a squaring function on numbers, square of 3 is 9, this lifts automatically, implicitly, to vectors as well. So you can square the vector 1, 2, 3. And that means 1 squared, 3 squared, 9 squared. And you don't write map square, you just write square. Square is lifted automatically to work on that vector. And not just vectors, but multi-dimensional collections of things, arrays of things. So it works on matrices and cuboids and so on as well. So squares and matrices and cuboids as well. So I mean, these are multi-dimensional arrays of things. Similarly for binary operators, so you can add two numbers, 1 plus 4 is 5, but you can also add two vectors. 1, 2, 3 plus 4, 5, 6 is 1 plus 4, 2 plus 5, 3 plus 6. So it's a pointwise addition of these two vectors. And again, you don't have to write anything different to get that effect. Addition, you don't have to write zip with plus, as you would in Haskell. It's just addition. And similarly for matrices and cuboids and so on. And similarly for things that are not just pointwise. So there are things that take arrays to values, vectors to values, collections to values, like sum. The sum of the vector 1, 2, 3 is 1 plus 2 plus 3, which is 6. Prefix sums, so the running totals in computing the sums is 1, 1 plus 2, 1 plus 2 plus 3. So that takes a vector to a vector. In APL, these are called reductions and scans, and that's where the terms scan L and scan R and Haskell libraries come from. They basically come from APL. So those are the sort of the flattest types you can give those two operators, sum and sums. But they too lift implicitly. So you can sum a vector, but you can also sum a matrix, and that doesn't sum up all the elements of the matrix. It sums up each of the rows in the matrix. And similarly, you compute the prefix sums of a matrix, and that runs along each of the rows in the matrix. So you get prefix sums of 1, 2, and 3, and on one row, and separately the prefix sums of 4, 5, and 6 along the second row. And again, you don't have to write anything to lift these. The lifting happens implicitly. APL's successor language, J, had also a re-ranking operator, which one of the things APL is also famous for is its bonkers notation. So this re-ranking is written with a double quote subscript 1, apparently, in J. But the idea is to take a row-wise operator, like sum or sums, and make it a column-wise one instead. So re-ranked sum on the matrix whose rows 1, 2, 3, and 4, 5, 6 is doing the sum on the columns on the 1, 4, 2, 5, and 3, 6. So that amounts to transposing the matrix and then doing the ordinary sum along the rows of the transpose matrix, and that gives you a vector. But it's the column-wise sums rather than the row-wise sums. And similarly for computing the prefix sums, a scan, you transpose it so that when scanning along the rows, you're scanning along the columns of the original thing. That gives you a matrix, and then you have to transpose the result back again. So what you write in Haskell in terms of functions like transpose is written with this funny re-ranking operator.
Question?
Yes?
Why do you insert a transpose on the second row but not on the first one?
People always ask that. So to a linear algebraist, row vectors and column vectors are distinct things.
Yes, me too as well.
But to APLers, they're not. They're one-dimensional things. So
is there an implicit transpose on the first one that you just didn't?
No. So this sum by itself takes a vector to a scalar, and a two-dimensional thing to a one-dimensional thing. It loses a dimension.
Yes.
Whether you do it on rows or on columns, it loses a dimension. So it takes a two-dimensional thing to a one-dimensional thing. Now I've drawn it as a row.
Yes, but it should be drawn as a vector.
I've drawn it
but it's the same thing in APL because
there's no distinction between a row vector and a column
that's
vector.
because it's one dimension.
Because it's one dimension.
So there is
the thing that I've written transpose here is something that only applies to two-dimensional or higher.
Or mark, yeah. So in a sense, okay. Thanks.
And in general, you can do this re-ranking not just on dimension 1, but if you have a multi-dimensional thing, you can re-rank to any of the dimensions.
So in the APL, if I have two dimensions, but this last one is 1, that's implicitly going to be reduced to
there's no distinction between an n by 1 matrix and an n vector. And similarly, no distinction between a 1 vector and a scalar.
So the transpose is just the identity?
Yes. So the transpose will just be the identity.
So I would just put kind of transpose there and put the implicit conversion back to it.
Yeah.
And it's uniform.
Okay. When you give the talk, you can do it that way.
I will. When I'm not confused, I won't laugh.
So there's another. So it gets more interesting because the arguments of the binary operator need not have the same rank. So the rank is the dimension. So you can add a scalar to a scalar, you can add a vector to a vector, you can add a matrix to a matrix, but you can also add a scalar to a vector. So adding the scalar 3 to vector 4, 5, 6 morally amounts to lifting the scalar 3 to a vector, all of whose elements are 3, making the vector 3, 3, 3, and then doing the vector addition. Or you can add a vector in a matrix, or you can add a scalar in a matrix. There's this kind of implicit alignment of the two argument types to the smallest, to the least enclosing type before you do the operation. However, the shapes at common ranks must match. So you can add a 3 vector to which way around am I doing this? A 3 by 2 matrix, and that makes sense. But you can't add a 4 vector to a 3 by 2 matrix. That's a shape error. So the question at the back.
Yeah, suppose we're adding a 3 vector to a 3 by 3 matrix. How would it know whether we wanted those copied across rows or columns?
So rows are primary. So you'd have to re-rank it if you wanted to do it on the columns instead. So there's an interesting question here about what things are allowed and what things are not allowed. And in APL and J, it's all dynamically resolved. So you get runtime errors if you try to do bad things, and no runtime errors if you don't. And it would be nice to know statically what's allowed and what's not. The fact that you can do this alignment, but there's some constraints on matching parities and stuff, makes it less than obvious which things should work and which things shouldn't. So there was a very nice paper from ESOP 2014 by Justin Slepak and co. on making a static type system for languages like APL, an array-oriented language. So they introduced a new language called Remora and provided a static type system for this, for specifying what's allowed and what's not allowed. And it's a type system, so it's got lots of syntax rules and type judgments and kind and index judgments and small step operational semantics and stuff like this. So all done PLT regex, so it's all this is nicely formatted LaTeX, but this is generated from a schema-ish model of syntax and typing and so on. But they've had to put a lot of work into building this type system, and they haven't finished with that because it's a separate system. It's a model of their programming language. They've implemented this programming language, and they've implemented a separate model of what are good programs and what are bad programs. And my thesis is that was unnecessary work, or at least work that is not as reusable as it could be because it's done in a separate notation. We don't have to make a separate model of what it is to be well typed because we have typed languages that let us capture in the language what it is to be well typed in the type. You don't need to build your own special purpose type system for a particular class of things because we have sufficiently general purpose type systems that will allow us to do this now. So I'm going to show you roughly how this works. I'm going to use Haskell as well, because like Sam for me, for it to be nice, it has to be in Haskell. But it doesn't have to be in Haskell. Scala would work too. The important thing is that it should accommodate higher ranked things like maps and like functors and so on, functors and applicatives. And I'm not going to assume that you're all Haskellers. I'm going to try and make you all Haskellers. Maybe that's ambitious. So the idea, and what Sam hinted at in his talk, is that these days Haskell is on the way to being a dependently typed programming language. There's a familiar data type of natural numbers. 0 is a nat, and s takes nats to nats, so it's a successor function on nats. That makes a new data type nat, and new values, s, z, which is a constant, and s, which is a function. But that's, in Haskell, that automatically gets promoted to, as well as the data type with its values, a new kind and its types. So there's a new kind also called nat, and new values, well, sometimes called z and sometimes called s, also sometimes called quote z and quote s. That's a slight wart. I don't like that syntactic convention, but sometimes you have to disambiguate, and sometimes you may disambiguate, and sometimes you can't disambiguate in a language. It's a bit clunky. But anyway, this makes z a type as well as being there's a different thing called, well, I'm going to call it quote z throughout the talk. Quote z is a type, representing at type level the number 0, and quote s is an operation on types, representing at type level the successor function. And nat is a kind, so just as types have values in them, the things that have types in them are called kinds in Haskell. And this allows you to define vectors, length index vectors, as a Haskell type. So vectors, so these are vectors where there's an element type, so it can be vectors of integers, vectors of characters, vectors of booleans, and so on, but also a size. So that you can have vectors of length 0, vectors of length successor of n for some n. So the length of the vector is encoded in its type. So these aren't proper dependent types. These are not types that have value indexes. That's why I had to make a type level image copy of the natural numbers in order to have the natural numbers as a type. So that's why Haskell is not really a dependently typed language. It's kind of faking it. But now the shape of the vector is encoded in the type index, the first parameter. So vectors take 2 parameters and yield a type, and the second parameter can be an arbitrary type, so it's a polymorphic. Vectors are polymorphic, you can have vectors of anything. But the first parameter can only be a nat, things of kind nat, so you can have vectors of a length, but you can't have character or boolean or lists of strings or anything like that in that position. And this says v0, the empty vector, is a vector of length 0, and vcons takes an element and an n vector and makes an n+1 vector. And so there's fancy stuff in the types, but the values don't need to be very different. So this is a constant, a value v1 to 3, and it's made by consing 1 onto consing 2 onto consing 3 onto nil, just the way you would make a list of length 3. You can do pointwise application. So here's vmap that takes a function, an a to b function, and a vector of a's and makes a vector of b's. And again, the value level is defined just the way for length index vectors as it would be without the length index, just as it would be for lists. And similarly for lifting a binary operator, so this is v zipwidth that takes an a to b to c function, and a vector of a's and a vector of b's and makes a vector of c's, and applies the function pointwise. So it takes the first a and the first b and adds them to make the, or does whatever the function does to make the first c. But note the benefit of the length indexing here. The zipwidth takes a vector of length n of a's, an n vector of a's and an n vector of b's, and makes an n vector of c's. So the length of the result is the length of each of the arguments, and it's a type error for the arguments not to have the same length. So what would be a runtime shape error in APL is a static type error in this model of vectors. And that's basically the trick. And Sam has type level naturals as sizes of things. So that's all very well for map and zip. The gadget you need to do alignment, if you want to combine a scalar with a vector, is kind of replicate. So this is the thing that takes an element and makes a vector of the appropriate size of that element. So replicate takes an A to a vector NA. And you want to be able to do that for any suitable type parameter n, which is to say any suitable type level natural n. And the way you do that in Haskell is by making a type class of the n's for which you can do that. I'm going to call those n's count, maybe countable would be a better name. So the type n of kind nat is a count type. If you can give me a suitable definition of vreplicate that takes an a to make a vector NA, an n vector of a's. And 0 is a suitable count type, and when n is a suitable count type, then the successor of n is a suitable count type. And this is how you define the vreplicate for each of those. So this says, in fact, that all types of kind nat are suitable count types. I can't actually express that in Haskell. This is an open definition of which ones are countables. But the Haskell type checker is not sophisticated enough to work out that this means all nats are. But collectively, all these instances give me a way of turning an A into a vector of NAs for any count type n, which I can see, although Haskell can't, is any nat. So if I wanted a 3 vector, I can just say, give me so if I wanted a vector of all of whose elements are 3, I can just say, give me the vector all of whose elements are 3, and which one of those I meant is determined by its type. So an interesting observation here is that I'm using the types not as many programmers with impoverished views of the world see it as a sort of a nanny thing telling you not to hurt yourself and stopping you making errors, a protective mechanism. The types here are used as a generative mechanism. They're used for reducing the right programs. So types are a positive thing as well as a negative thing. And not just for catching errors, I can tell you a lot. Colin McBride is very big on making this point. People ask what types are for, and they say, well, they stop making stupid errors. And no, that's what types are against. Types are for this thing.
Good question. Can you also do IOTA, for instance, index space with the...
Can you also do?
Like IOTA, From 1 to...
Yes,
or
yes,
0 to
yes.
1?
And in fact, we'll have one of those in a minute. So this is the thing that give me the vector 0, 1, 2, 3, dot, 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 n through whatever the length is, yes. It's a little bit trickier, but you can do it. For things like sum, which traverse a collection and collapse all the elements of it, collapse together all the elements of that collection, in Haskell those things are called fold. So for that you need something analogous to the fold for lists, but for vectors here, and so I'll give them one that's the definition is precisely the same as that for lists. So you can do things like summing a vector and computing the dot product of two vectors and so on. And similarly for traversing, things like sums, so that's specifically a left to right traversal. The way this is done in Haskell is to do it for any what's called an applicative functor. I'm not going to get too much into that, but this allows you to do effectful computations for each element. You can do I/O stuff for each element, or stateful things for each element. And you do them in a particular order, so the effects are chained together in a particular order. So in particular, so here's a stateful thing that operates on an integer state, takes an integer input and produces an integer output. So when the input is n, you get from the state n, you write n plus n to the state and return n plus n. So this is just adding to the state and returning that sum. And if you do that across a vector, you'll compute the running total. So this will compute the prefix sums of the vector. So the run state is a bit clunky, but this kind of stateful thing is enable you to do scans over vectors. This is the not quite. So the important thing about vectors is each vector type, vector n, has a corresponding type of positions in the vector. So I'm going to call that fin n, so it's the finite type of size n. The vector of length n has n positions, so this is a type. Fin n is a type with precisely as many values as there are positions in the vector. So it's precisely the right type to use as an index type for indexing to the vectors, because there are just as many indices as there are valid ways of indexing into the vector. So this is again an index type, fin n for a given n. So there's no ways of making fin zeros, so there are no elements of type fin 0, that's the empty type, that's the type with no elements, that's good. And there are two ways of making fin of the successor of n. There's a constant there, and there's one way of embedding the fin n into the fin successor of n. So if you think about it, this gives you precisely as many elements in type fin n as the natural number n. And so this, now we can do lookup in vectors. And it's a type-safe lookup, so I can take a vector of A's and an index and pick out that A, pick out the third element of the vector. But the index is precisely the right type for doing the indexing, so it becomes a type error to try to do an out-of-bounds vector index. Conversely, tabulation inverts this. So the lookup takes a vector NA to a fin n to A, and this is the kind of representable thing that bolted into that. And that transformation is invertible. You can take a fin n to A back to the vector n. And what this does is works out the iota vector that Martin asked about, the vector 0, 1, 2, 3, and applies this function f to each one of those positions and gets the corresponding vector back. So if you know what element you should have at each position, you can work out the corresponding vector. As for re-ranking, so if you want to be able to compute sums over the columns of an array with a matrix rather than over the rows, well, then you, as the diagram hinted earlier, you want to be able to transpose these things. And how can you transpose a two-dimensional collection? Well, the neat trick is via this conversion to lookup form. So via conversion from a manifest collection to a collection represented as a function. So these are called pull arrays in Feldspar, or I can't remember which ones are pull arrays and which ones are push arrays, but you could represent these collections as functions from indices. Well, if you have a collection of collections, you can turn it into a function from indices for each of the two indices, and that's a two-argument function. And it's easy to transpose that because you just transpose the two arguments of the function. So these two things here turn my m vector of n vectors into a function of type n to a, and then I flip it to make a function of type n to a, and then I just put it back together again. So here's a picture of that. Doing the two lookups turns my manifest matrix into a function from a 3 set to a function from a 4 set to n, and then you just flip that to give you a function from a 4 set to a function from a 3 set to n. And then you retabulate. So morally, that's what transposition is. That's not a terribly efficient way of doing it, so because there's lots of data movement there. So you might want to represent your collections in this form in the first place. So that's the representable functor representation. Now, everything I've told you about vectors is not specific to vectors. So you can, and APL does, say that each dimension of one of these matrices is a vector, so you have essentially 3 vectors or 4 vectors and so on. But there are other things you could admit as the dimension types of these collections. For example, pairs. So vectors are pairs, and pairs are vectors, and pairs are pairs, and so on. Those are a perfectly good component for multidimensional things that support all the operations I've shown so far. So in Haskell, you abstract that into an interface, and again, it's a type class. So the usual type class for being able to map over things is the functor type class, and vectors are a functor, but pairs are also a functor. You can think of these as container types. The thing you need for replicating, the thing you need for zipping, pointwise addition, are what it is to be an applicative functor. And vectors are applicative functor because, as I showed you, you can do replication for vectors and you can do zip width for vectors. But pairs are also an applicative functor, and here's how to do replication for pairs. You just get 2 copies of the thing. And here's how to do zip width for pairs. If I have a pair of functions and a pair of arguments, I can make a pair of results, applying the functions to the arguments pointwise. So now, more than just a container, it's a container with positions for its elements. But other things are containers with positions for their elements as well. Here's Patrick Janssen was doing some work. For some reason, I've lost track of now, but on using block-structured vectors. So block-structured arrays. So a block-structured array is a block-structured vector and block-structured vectors. And what's a block-structured vector? Well, it's like a vector, except that rather than these things necessarily being an element after an element after an element built with constants, they're ones that you split up into blocks. So they fall apart neatly in the middle rather than taking the first element off. So there's a singleton block vector, well, there's a singleton block shape, and there's a concatenation of block shapes, a join of block shapes. And then a block vector is a collection of things indexed by block shapes. And there's a 1 vector that's indexed by the singleton shape, and there's a plus of 2 vectors that's indexed by a join shape. And these block vectors are containers with positions as well. So you can do the mapping, and you can do the replicating, and you can do the zipping for these block vector things too. for transposition, the essence is this conversion to and from the function form. So taking a collection of A's, an f of A, and turning it into a function, and turning it back from a function into a collection, a manifest collection of things. So for that, remember for vectors, we needed to take an n vector of A's to fin n to A's, so there's some relationship between n vectors and fins, fin n's. So that relationship is captured by an associated type in Haskell, and the transposable things are, it turns out, precisely the Naperian functors, so that explains the other bit of the title of the talk. But what's a Naperian functor? It's a functor f, which should also be applicative, but most importantly, it's an operation on types that has something analogous to logarithm. Why logarithm? Well, it's because these things behave like logarithms, and they have the properties of logarithms of products and logarithms of composition and so on, so it's a very natural analogy. Why Naperian? Because John Napier invented logarithms. Why the name? That's due to Peter Hancock made this observation. But an Naperian type is one with an associated type of positions. Look up and tabulate the transforming between these two formats. As it happens, there are two ways you can specify one of these components. So you could define this tabulate function, or you can define the position if this is the iota kind of thing. In fact, for vectors, I define tabulation in terms of positions, but you can also define positions in terms of tabulation. So then, provided you've got two Naperians, f and g, you can define transposition. Transposition takes an f of g of a's to a g of f of a's, and it's the same kind of thing. So now, not just containers with positions, but containers with positions of a fixed shape. These Naperian functors are f are container types f, where there's all things of type f of a have the same shape. And there's a type that tells you what that shape is. I'm running out of time, aren't I? So to do things like sum and to do things like sums, you need more type classes. So in the Haskell universe, they're called foldable and traversable. And these basically mean that the positions in your shape have to form a linear sequence. You have to be able to talk about the first thing and the second thing and the third thing. So an array dimension is a traversable, foldable, Naperian applicative functor. But since Naperian functors are necessarily applicative and traversable functors are necessarily foldable, two of those properties are redundant. So traversable Naperian functors. So that's why what I defined to be the dimension. I'm eating Dweger's time, so I should cut to the end, I guess.
Yeah, probably.
So let me say no more than from this you can build a multi-dimensional thing. So you make a data type that has type level vectors for each of these sizes. So just as you can have 3 vectors, you can have 3 by 4 vectors, matrices. And you can do all the replicating and zipping and so on these. And you can align them, and this is how to do lifting. And you can do somewhat cleverer things as well. So the replication, let's say to add a 3 to a vector, you make that 3 into a vector of appropriate length and have them pointwise. But it's wasteful to do the replication and then just use this different values from different places, which should just be replicated so it's always the same value. So a better way of doing it is to only symbolically make the replicated vector. So you can say this is a vector of appropriate length, all of whose elements are the same, and only store the element once. And you can capture that in the type information too. You can make flat representations of these things. You don't have to manifest the elements as a collection of collections. You can manifest them as a single array and have the shape sort of imposed on that array. I'll stop there. My ambition for doing this is to connect Haskell types that constrain the shape to something like accelerate. But I'm inspired now to say that what I should be connecting it to is PyTorch, and maybe we should talk.
Cool. I don't think we've really got time for questions, sorry.
That's my fault, sorry.
Maybe after Ava's finished, we could, if we have enough time after Ava's questions, maybe Jeremy, are you gonna